All right, moving on to problem statement 2. We've got the population of a small Texas town that is decreasing each year. That word decreasing automatically tells you this is most likely going to be a decay problem. So I take my equation, y equals 4,500 times 0.6 to the x power. And let's go ahead and type it in. 4,500 to the 0.96 to the x power. Go to the table, and let's use a table to fill in our missing values. So we've got 4,500, then 4,320, then 4147.2, 3981.3, 3669.2, and 3522.4. Now, important to keep in mind here that we are talking about number of people. So these decimals here, kind of have to take those with a grain of salt. You're not going to have 0.2 of a person. You can't have just an arm, just a leg, that sort of thing. So, yeah, in all reality, this is just 4,147 people. Now, to make the graph, we have to go ahead and label and scale our axes. First thing, our independent variable is always going to be the x value, or the horizontal axis. So this one is number of years. And then going up and down, we've got the dependent, or the y variable, which is the population. For the scale, this one's okay for it to go by ones. 0, 1, 2, 3, 4, and 5. This way, well, I got to go all the way up to 4,500. However, also the smallest one that I'm going, yes, sir.
Isn't like 4 supposed to be 3822?
Isn't 4 supposed to be what?
3822.
Oh, yeah, that's right.
Did I get off?
Yeah.
3981.3. Oh, I jumped one, didn't I? Okay, thank you. So 4 should be 3822.1, and then 6 should be 3522.4. No. Off again. 3669.2. Okay, that's better. Now we got to decide how to scale this axis right here. One option is going to be to start at 0, go all the way up to 4,500. However, we don't need to go that far down with this population graph. We could start this thing at 1,000, 2,000, 3,000. It doesn't matter. I'm going to choose just to go ahead and jump by, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I say let's just jump by 500s. Make each of these guys, each one 500. So 1,000 is there, 2,000 is here, 3,000, 4,000, and 5,000. So 0, 4,500, 1, 4,300, 4,100, 3,981, 3,682. So it's going to go down there. And there's our graph. Okay, now part A, what is the initial amount? Initial is always starting value, or what we had when x equals 0. So our initial amount is 4,500. Also keep in mind that when we did our growth and decay equations, the initial amount, the p value was always the one out at the very beginning. So 4,500 still tells you the initial amount there. Okay, what does it mean in this problem situation? Again, I don't want you to tell me, oh, it's the initial amount. Please tell me something about the problem. Here we're talking about population, so the initial amount would be the number of people. Okay? The number of people I'm off. The number of people when you started following the town's population. Just basically whatever, something to let me know, it's the initial population that you started with. All right, what is the growth or decay factor? Now, we talked about in our equations that it was A equals P times 1 plus R to the T. This guy, the R, is the rate. The whole thing underneath is the factor. So, the R is the rate. The whole thing, 1 plus R, is the rate. Is the factor. Which means that this thing underneath the variable is the growth factor. So we look here. Well, not growth factor. In this case, it's decay factor. 0.96 is what's underneath the exponent. So the decay factor is 0.96. And is this an example of growth or decay? Well, decay. And reasons for that: it decreases over time. You could have also put the factor is less than 1. Anything that let me know that you know why it's going down. Now, what is the approximate value of the boat? Oh, we had a small typo here. That was from something we changed in the problem. I forgot to change that. It should have said, what is the approximate population after 5.5 years? Well, in that case, all that we have to do is plug it in. 4,500 times 0.96 to the 5th power. 5.5 power. Me 3,595 people. 3,595 is the population.